Well, thanks so much for having me. I'm really thankful to the organizers. But I hate to be in this place. I'm in between you and lunch, and that's a terrible place to be. I'll do my best to make it worth your time. The title of the talk was originally going to be a lot about coarse-graining. I've seen that there is already a little bit about coarse-graining in the conference. Based on the questions that I saw earlier, and I think the broader interest of this workshop, I'm going to talk a little bit broader than that, and then dive deeper into what we've specifically done in coarse-graining. But the grander vision here is something that I think most of you will agree, is that we need new materials fast. And this is very much in the spirit of the Materials Genome Initiative. How do we go around finding energy generation, energy storage, transportation, green chemistry, remediation of damage we've done so far? We're going to have to go back and fish all the plastic out of the sea. We're going to have to get all those heavy metals out of the water. So how do we move around? How do we make those materials? And of course, I showed this in Korea. It really sort of hit a bone there. These are two places where machine learning has really outperformed humans at a speed that we wouldn't expect it would happen. So the question is, how does this look for materials design? How can we borrow this outperforming humans in design in these sort of games where the rules are laid out, right? The rules are there, so it's not too difficult to have a computer through some clever mix of rule-based and learning-based approaches beat us at some game. How does that look for chemical or materials design? And I would say, come from this right-hand side here, computers can help us in materials through a continuum that links simulation and statistical learning. On the simulation side, we've got all sorts of rules of the game, that's physics, that explain what a material will do or what a chemical system will do. And there is a lot of advantage in physics-based simulation, right? It can be cheap, not always, but it can be cheap. It can extrapolate as long as your laws hold. It can give you out-of-the-box solutions because, again, it can extrapolate. But it's as good as the model. So if you don't put something in the physics, it's never going to show up in your answer. And it can be very costly. We've heard about electronic structure, for instance. That's one kind of expensive simulation. In general, fluid dynamics, too, can get costly. And I would say in the opposite end of the learning curve, in the opposite end of the line, there is machine learning. There is statistical learning. Let's throw just data at the problem and use statistics to have come up with an answer. And we've seen that perform really well in some tasks, right? It's very fast. It can use a lot of data. So if you have a lot of data, it's very useful. But you need the data. If it's somebody else's data, then there's no machine learning. And I think for the theoreticians here, this is a constant with discovery, right? And that's why we sometimes turn up to bootstrapping with computational, with simulation data, because there isn't really that much abundant open source experimental data. So what we're trying to navigate, and I think is in the spirit of this conference, is what is this continuum of learning and physics-based simulations to move around. And I would say material science, I was trained a chemist. I'm now moving broadly into material science. And I would say there is a problem that is common, I would say, to the machine learning challenges for material science, which is the multi-scale issue, the multi-scale nature of the materials, of the systems we're interested in. And I would say, from the physics simulation side perspective, you could think about toy quantum models where you've got really big mathematical tools to simulate with extreme accuracy, small problem, atomistic simulation with electronic structure, molecular dynamics, coarse-grain molecular dynamics, on all sorts of continuum models for transport, for optical properties. And that ties into representation of the systems we're trying to learn over. And we saw tons of questions about features earlier. It's like, how do I put my system into a machine learning model? And that's, I think, I wouldn't agree that it's a solved problem. It might be somewhat for chemical atomistic simulations, but it's not throughout, right? Like maybe you care about grain boundaries, maybe you care about photonic properties, and in those cases, the way to input the system to machine learning is an open question. Most of what I've done and most of what I'm going to present is in the realm of atom-based features, atom-based descriptors, and somewhat ties to what we've heard so far. And the way we came into machine learning was through the simulations. And this is the idea behind high-throughput screening, which is, again, something that is very materials genome. And the idea here is, you make up a big box of virtual materials that you're interested in. You know what you care about. You enumerate everything that's in that space, and then start throwing simulation at them. It could be periodic DFT simulations if it's a crystalline small system. It could be molecular dynamic simulations if it's soft matter. It could be any type of simulation as long as you can move through a database of boxed candidates. You simulate some of those look good, you pass them on to an experimentalist to make, and feedback whatever they tell you, right? That's a cycle that has more or less been established in places where we've got good simulations, and we fix them up with machine learning a little bit. And these are two stories, one in organic light emitting diodes, one in flow battery materials. I won't get into the specifics, but I would say this whole sprinkle machine learning in the bottom-up simulation to experiment cycle has worked out pretty well in these instances. And it also allows us to map chemical space. We found for different properties. This is OLEDs. This is a beautiful Pareto frontier. We would like to be up here. This is molecules for flow batteries, stability and properties we care about. In this box of molecules, there's plenty of stable, good molecules. In this box, there isn't really that many. So this big data approach, has enabled us to map tons of chemical space, but also gave us the data to actually try or start doing machine learning over. And I would say the first machine learning tasks that show up here are bypassing these expensive calculations. We had a bunch of those examples already today, which is, I'm bootstrapping tons and tons of first principles data. It's costing me a lot of compute time, and I would like to move around this space faster. Just train a system that will tell me if my calculation is worthy or not. If my system is predicted to be absolutely terrible, I don't even want to waste an expensive calculation on it. And I would say the not completely solved challenge here, depending on the nature of the simulation, is representation learning, how you input your system. And I would say if we're moving in a low data space, typically coming up with features that we know reflect the physics, we know reflect the invariances, is the general strategy. If you've got 100, 200 data points, it's typically very common to say, I know electronegativity is going to matter, an atomic radii, and a number of s electrons. So you pull all of these descriptors from your bag of physics variables that matter to you and train on that. And that's a strategy. It ties really well when you have little data and you want to be sure that your system will be robust and hold that. It will transfer better, and in general, it's the more low data approach. Now, if you've got hundreds of thousands of data points, and we've heard that about machine vision today, it's usually better to go to a raw representation, to a more basic representation, particularly if we're talking about design. If you want to optimize over something, ideally the input of your system would be a degree of freedom, would be something that you have freedom over. It would be a knob that you can move, right? You cannot invent new electronegativities, right? You can choose in the periodic table, so your input should be something that holds these degrees of freedom that are available to you. In molecules, say you're trying to make a new drug, well, you've got control over the drug structure, the molecular graph, but you don't have control over the 3D configuration. The 3D configuration will emerge from the graph, and we've heard about this 2D to 3D mapping. And as this came up today too, I would say there is, I think, a little bit of what should I train over. QM9 is, I think, a great testing benchmark, but it doesn't really represent an ensemble of chemistries. It's a grid of every possible compound you could make. So it looks a lot like the box idea, but it's not a representative sample of molecules you could make, or molecules you could buy, or molecules that represent some distribution. And same to do dynamics. When you're thinking about moving around a space, it's typically good to have a training data that is a true sample of some underlying distribution. Otherwise, and we've seen this happen oftentimes, you're just pretty much picking up the nearest neighbor in your system and not really interpolating much across that space. I would say the toolset that we found works really well for us in representation learning for molecules/crystals is the message passing neural network framework. And the idea here, I mean, if there's physicists in the room, maybe the embedded atom method sounds familiar. The idea here is to label each atom in your system with some initial set of features. Ideally, would only be the atomic number. So that's the only thing that nature really, maybe atomic number. If you're into isotopes, then maybe the isotope. But in principle, the actual degrees of freedom, the integer atomic number, is something that you're actually allowed to choose from. And then each atom gets a bunch of information transferred from its neighbors. Its state gets updated, and we repeat this cycle a bunch of times as we move outside the graph. So essentially, we featureize the system with atom labels that influence, that capture all the farther out contributions. So the places to tweak around here is what initial message function, how does this message function get combined to the other neighbors, and how we create a whole feature for the whole system. And there is tons of flavors, tons of ways to do this. Typically, it's shown really good performance for molecular, and there is also a crystal graph version. And it needs about 1,000 to 10,000 data points. So if your problem looks less than 10,000 data points, it's probably better to embed some of your prior knowledge about the physics beforehand. And as I said, there is all sorts of special tricks, skipping some nodes, so you go out faster. There is a version for crystal graphs, for periodic systems. You can make edge updates. You can featureize edges so that they hold distances. So now it's become a 3D representation rather than a 2D representation, right? The amount of information that passes through is mediated by the real space distance. So there is tons of flavors, but it's typically a good representation learning scheme as opposed to, let's say, featureize with physics by hand. What is the use of this? As I was saying, we can move through these databases faster. And this is an example of sampling strategies going from sort of more first principles Thompson sampling and a bunch of just epsilon greedy. Sometimes we do what the neural network says is best. Sometimes we do totally random through our database. And in general, pretty much everything is a good idea rather than going around sampling randomly. In our experience, the active learning strategy doesn't matter as much as having some active learning strategy to move through our closed space. So this is great. We've got a database and we can move our way over it. We got some theory. Maybe we make the theory better with empirical corrections with machine learning. That's cool. But again, we need a box of search space. And the whole spirit of, I think, of today's session is how do we do the opposite? How would we, rather than going through a list of candidates saying which is best, how do we, for a given task, find out what the answer is? And for some people, this is just called optimization. But I think for, in this community maybe of materials discovery, I would say this is inverse design. The idea would be to have a surface function, have a response function over your search space that can be invertible, or at least maybe give you gradient descent, where you can do a smoother optimization than your traditional trial and error or high throughput flavors. And this is where we borrow from deep generative models. I would say they've shown this uncanny performance I've been talking about, right? This is how the needle has moved in a couple of years for deep generative models, and it's only going to get better. So it's a very powerful tool to come up with new members of some distribution without ever having had to enumerate or fully understand what the distribution is, which is something that looks very good for molecules and materials, right? Like there is an underlying distribution of chemistries that is hard to lay down with words, and maybe it's just embedded in the examples of the molecules we've made so far. So the approach here, and you've heard about variational autoencoders already very deeply, so I'm not going to go too deep into here, just say we can get a discrete object, send it to a continuous space, and then continuous optimization is way easier. It's a lot easier to take gradient-guided downhill steps in this continuous low-dimensional representation, solve our problem, and decompress what the true answer is. And these are some examples from one of the first implementations. This is mutations of aspirin, so just encode aspirin, make a little wiggle in continuous space, take it out, and you see we get these chemically sensible mutations of aspirin, right, that are inspired in sort of what the chemical noise, what a small chemical change means. For molecules, it gets translated into a small numerical change in a continuous space. Same thing, we can sample random numbers and see what molecules they become. This is a library that was trained for OLEDs. So just sampling random numbers gives you random molecules, and they all kind of look like the organic light-emitting diodes that we were going after for that project. Moving in that space is tricky. We've talked about the Euclidean distance, but of course, as your system is a multidimensional Gaussian, actually linear interpolation is not the best tool to move around that space, and we've seen that spherical interpolation works much better. And the spirit here is that starting from one molecule, as you go further out, that looks terrible, doesn't it? As you go further out, more chemical noise becomes larger distance in the latent space. So it gives you a way to essentially build structure property relationships, let's say structural relationships in the latent space. And as we've heard today, if we're optimizing, we're still missing one thing, right? We can come up with new members of the distribution, but they don't really do anything, right? We're just sampling randomly things that look like molecules. We want molecules that do something, right? So the idea now would be to add supervision to this unsupervised approach so that we know for a latent point, not just what molecule it's going to correspond to, but what properties we should expect there. And again, we come up to the big data problem, right? Building these algorithms is going to take tens of thousands, hundreds of thousands of data points. So it's probably not the approach you would take for something that you can only run a few experiments over. But in many molecular systems, particularly we're running simulations, we do have this data. And I've got this colorful plot that maybe remembers some of the things we've seen earlier, which is this is a naive, unsupervised, here in the left, there's a naive, unsupervised autoencoder, and we're coloring by property. And you can see that even though it learned structural similarity, a point next to aspirin looked kind of like aspirin, it hasn't learned structural property relationships at all, right? We've ended up with a system that has learned structural similarity, but it hasn't learned structural property relationship. The space is pretty much randomly distributed for properties. And then this is a multitask, so we supervise the system with learning multiple tasks, and you can see how for each task, the space now has a clear direction, right? So in this space, it's way easy to optimize, right? Like you can just look at it and know what direction you need to follow to optimize, right? You would want to go left, or top right, depending on the property that you care about. And of course, when we run a trial optimization for this, it's pretty easy to find the global optimum over our search space really, really quickly, right? This is how a random search or a genetic algorithm or just building a Gaussian process on top of this surface looks like. So in principle, we've got a inverse design tool over discrete objects. And this, of course, has attracted a lot of interest across the community. A word of, because I think most of the people here care about practical applications, I would say, you can see, right, like these machine learning generative phases kind of work, just like this phase method of chicken works, right? Like, we're really good at fixing up the mistakes of the neural network, right? It's very, just like that mountain in Mars used to look like a face until they got a high resolution picture. But we need to convince people to make stuff, right? This is the idea. In the end, if we want to deliver new drugs, if we want to deliver new materials, we're bound by the physicality of the world. And a pixel change could be tolerable in an image, but an atom change, right, changing carbon with arsenic is definitely not going to be tolerated. So there is an outer optimization that is not captured in these algorithms. And I think this is where some of these next steps are going. And so people like Rob Lowe would argue that coming up with new stuff, coming up with thousands of new candidates was never the challenge in the first place. So I think the practicality and the physicality of this is something that will need domain expertise to embed those things that are not obviously captured. And of course, I've put this mostly for the, because I know the slides are going to be shared. So there's been a lot of new updates we've heard about different ways today of also doing this idea. There is GANs, there is tons of flavors of new ways to do this better than what I've shown. And then, as promised, a little bit of coarse-graining. And what is coarse-graining? I mean, as far as we're seeing it, is dimensionality reduction, maybe for inverse design, maybe just to have fewer dimensions to simulate. So it kind of looks a lot like what I just said, but in 3D. Right? The idea of coarse-graining, where you're doing an atomistic simulation, is taking up your all-atom system and deciding that there is a series of atoms that move collectively together. They're pretty much always bound to each other. And in the grand scheme of things, you can represent them with a collective variable. Right? There is one superatom that could represent them all, and you would just move in the space of these superatoms. And this is something that has been done for many years. The theory of what's important in coarse-graining is pretty well understood. The information that gets lost is pretty well understood. The statistical mechanics of this have been laid out. But the algorithms to do it are tricky. There isn't really an intuitive, easy way to move around the space, to coarse-grain. So you end up with either you make custom solutions or you pull solutions from a table of folks that have coarse-grain for you in systems that are typically transferable and common. That would be in biomolecules. That's a community that does a lot of sample with molecular dynamics, and the building blocks that they use get repeated a lot of times. Right? There's only 20 amino acids to make proteins, so it makes sense to coarse-grain each amino acid as a sphere and work your way through that. But that's an arbitrary choice, right? Somebody decided that this is the set of atoms that, based on my chemical intuition, move around collectively, right? They all are bound to each other and get summarized together. But that's an arbitrary decision. So I would say, in our mindset, the coarse-graining idea, oh, I'm sorry about that. The coarse-graining idea is to come up with an end-to-end way where, starting from an all-atom system, identify what is the optional dimensionality reduction, right? Coming up with what is the way to compress those degrees of freedom into superatoms, and learning what the Hamiltonian, what the potential energy surface or the potential energy function is going to be in that reduced dimensional space, right? So given all-atom resolution, come up with the coarse-grain resolution, and given the all-atom energy functional, coming up with the reduced dimension energy functional. And if we're in the spirit of inverse design, maybe one more thing, which is knowing what actual 3D conformation is hidden inside the superatom, right? And then in that context, this is a variational autoencoder. This is an information bottleneck problem, right? Where we want to compress the system and then blow it up again, recovering whatever was inside. And in the process, we can learn the compression field end-to-end and the potential energy surface or the potential energy function end-to-end. So how does this look in practice? We start from, this is single molecule in gas phase. So these three groups are tied together and moving around. and they've got some complex energy functional in the all atom resolution, and then they get a coarse grain through a neural network that essentially has to do a task of assigning them to a superparticle. I won't get into the stat mech, but you need to have every atom has to correspond to only one superatom. So that you need to discretize. They can't be smeared out, and that has to do with momentum conservation. So we use Gumbel softmax. We use a discretization strategy so that at the beginning, you can see in the animation, the weights are all over the place, and as the gradients flow through and the neural network learns, and we raise the temperature in Gumbel and discretize the system more and more, we end up with a deterministic mapping, which each of the atoms in the phenyl ring gets put into a bead in the coarse grain representation. Right? And you can see all the C's, the set of C's go together, the set of H's go together, and in the bottom then we run a new trajectory in the coarse grain representation and see that it recovers the radial distribution function. In this case, it's just a molecule with 3 degrees of freedom, so there isn't really a lot of distribution, but you can see that it recovers the structure pretty well. I said this was a unsupervised or semi-supervised approach, so we can see what the coarse grain geometries correspond to, and they correspond to, interestingly, the mean. You can see the benzene rings on the left. It's not a perspective issue. They're collapsed onto their main axis, and the reason for that is we suppressed the information about their internal rotations, so now it's gone, and unless we put it back somehow, the information got lost, so the neural network just learned the mean positions, and the mean positions of those internal rotations is just their main axis. And there is very good tools out there for about 6 months to how to reconstruct this into a full-blown 3D with a Boltzmann population. So this is the next steps, how to have the decoder have a, let's say, Boltzmann average or a Boltzmann population and representative up conversion. But for now, our decoder learns the mean structure, and this is something that works for bulk simulations. This is a molecular liquid of ethane, so I think it was like a box with 250 molecules. We do all atom molecular dynamics, we get the trajectory, we train our coarse-graining and coarse-graining force field tool, and this is how the assignment goes. I think folks would have been able to figure this out by hand, that every CH3 makes one superatom. It's not always so intuitive. In the case of aniline, for instance, aniline is benzene with an amino group. Most people would say benzene is one bead, the amino group is the other, but that gives you very differently sized spheres that don't really capture the size of aniline. So you pretty much end up with, when you do it this way, with 2 equally sized coarse grain particles. And then in the case of ethane, you can see in the left, we trained a classical potential. The folks that do coarse graining typically want these very simple, very neat, very intuitive functions, the very intuitive Hamiltonians. So in the left, we have just a bonded term and Lennard-Jones. And you can see that it does its best to recover the radial distribution function. But there is some information loss in that potential energy function that can be recovered when one trains a neural network potential. In the right, I'm showing the same idea, only instead of coarse graining to a simple Hamiltonian, coarse graining into a neural network Hamiltonian using message passing neural networks like I shown earlier. And that, of course, recovers the radial distribution exactly. And you can see here in the A plot here that it essentially learns there is the pairwise potential of mean force is a very deep parabola, which is the bonded term, of course, but then it has a little kink to represent the second order solvation cell, right? This is the 3-body correlations that we've embedded into our 2-body Hamiltonian. So with this, I would say that, you know, for many of the problems that we're trying to do, there is a continuum between machine learning and physics-based model. Parameterizing physics-based model is a learning problem, coming up with what are the weights, the things that matter in your system. Maybe building up a physics-based model is a machine learning problem altogether. It's definitely a learning problem. What's important? What are the degrees of freedom that matter? And then I think for design, machine learning for materials is mostly an issue of representation. How do we put in these invariants, these symmetries that matter? For instance, I've talked about graphs. Graphs are great, but in chemistry, actually, we have, let's say, 2.5 dimension systems, because we care about chirality. There are internal rotations that are forbidden in the cis-trans isomerism, and our graph tools pretty much eat that, suppress that information. There is no difference between the R and the S graph, but there are big difference between the biological activity of R and S molecules. So with that, I would like to thank you again for your attention. I think I'm right on time for lunch, and thank the organizers for having me. Thank you.
Yeah, thank you very much, Rafael, for this very impressive talk. So here's a question.
Very nice talk. I have a question regarding the coarse-graining method. So you introduced this sort of dimensionality reduction approach to sort of group the atoms together, and it seems to work very nicely. But there's this open questions of how to choose how many coarse-grain particles to use, right? Because every time you fix this number, you have a lower bound of the systematic error that you introduce. Have you thought a bit about approaching this problem, sort of like when to stop introducing this?
Yeah, that's a good question. Mostly we've been thinking about these small organics that I think can be compressed. I think we haven't really gone too deep into that. I think it's an interesting area. You might be bound by the computational budget. You could break it down the other way around, say, my neural network, my graph network scales linearly over squares, depending on how you've written it, with the size of the system. I want to simulate a box with 1 million coarse-grain particles. So you could, for 100 microseconds, so maybe you could backtrack your budget and decide, you know what, I need a 10-to-1 compression. So give me my best 10-to-1 compression. That would be very sort of engineering. I think the first principles approach would be like exactly what you just said. Let's start turning the knob and seeing how it works. We've done that in other places. We've done that with this learning discrete spaces. And in general, encoders and decoders are so powerful, particularly decoders, that you can compress information a lot. Right? We've seen you can represent MNIST with literally three breaks down with 4 binary variables. It works, right? Because literally it's 10 digits. So if you got a representational capacity of literally 16 bits, it works. And if you got 8 bits, it doesn't work. So I agree that there is a knob there that we haven't really turned.
Thanks for the amazing talk. My question is regarding the first half, when you present so many mutations of aspirin and so on. So do you use any constraints or rules to first determine that this is a molecule that will actually exist based on, let's say, carbon can form 4 bonds and stuff like that?
Yep. We absolutely had to, particularly in the first generations of these. In our case, it was written as an outer loop that didn't live inside the end-to-end learning. So it was literally, well, if this is a 7 connected carbon, this is not a molecule, so it doesn't decode. The correct way to do it, and the way folks do it now, is embedding the rules of SMILES, and we heard about deep SMILES last year's paper. Embedding the syntax or the grammar, and as I said, in the corrections, there is also folks that try to write graphs straight out of a neural network. But yes, I think at the very least, if you're writing the molecular strings, it makes sense to write in the rules of your language inside the end-to-end learning framework, rather than doing it as an outer loop that sort of is decoupled from the back propagation.
And second question, in the continuation of what the gentleman asked earlier. So I'm confused if your encoder decides what is going to be the optimum superatom by itself, or do you use domain expert knowledge?
there's a lot of domain expert in the StatMech part of what's allowed and what's not allowed, but there isn't really any decision making other than the degree of compression, right? We have to say how many discrete particles we want, and that is the part that's a decision and has to do maybe with the computational budget or maybe with the accuracy. When do you start losing accuracy? But there is no, essentially, that's part of what the learning function does. It learns what is the optimal clustering, spatial clustering.
Okay, thank you.
Maybe I have a quick question. So on one of the slides that you mentioned that you do concatenation for non-additive properties, right?
Yep.
So can you push this through the coarse-graining steps essentially, or how do you have any issues with different sizes of the molecules then? Your concatenated property then has a different dimension, of course, different size.
Yes, thanks. That was a broader comment in the context of the message passing and making node labels.
Mm-hmm.
Typically, if your property is additive, it makes sense to just lump all the node labels together. If your property is very global and non-additive, then there isn't really a lot of advantage into compacting, and it makes more sense to keep the low dimensional, let's say low convolution information next to the higher convolution information, making sort of a longer fingerprint that comes up from the, say, first iteration, first shell, second shell, third shell. In coarse-graining, though, we're a lot more bound by the StatMech of what we can do. So pretty much, we need to compress the atoms together into a superatom that pretty much has let's say, a Hamiltonian, and we don't really have a lot of freedom there other than compressing all atom to superatom coordinates. At the end of the day, what we have is the superatom coordinate, which is a 3 XYZ, and the superatom contribution to the Hamiltonian, which could be maybe a discrete label, I'm atom type A, this is atom type B, or maybe even there is no, right, like in the ethane example, there's no classes, there is just one type of coarse-grain atom. So we literally have a 2-body Hamiltonian that learns 3-body contributions and coordinates. So in that case, we're sort of more bound by what the representation can be in the coarse-grain space.
Okay, thank you. So I see no more question. So then let's thank the speaker again, first of all. Thank you, Rafael.